Okay, so we're going to introduce our first dimensionality reduction technique, which is useful if you have numerical data. So at least the data need to be ordinal. So let's get some intuition between principal component analysis. Here in this graph, what we have is a set of two-dimensional data. Each average observation is plotted here as a scatter plot. We have two dimensions. Our goal is to reduce dimensions, right? So when we observe this data, we can see that along this x-axis, the data has a lot of variations. So we have the data range from here to all the way here. And the y-axis, the second dimension, it seems like the variation is smaller. It's only range from here to up here. And if we further observe, if we actually rotate the axis a bit, we can align this axis along the directions where the data has the greatest variance. And this gives us the red lines here. This again, two perpendicular lines. And you can imagine those is the rotation of our original axis or the rotation of the observation. But the key observation here is along this axis, this direction capture the majority of the variance in the data. And this direction captures the rest of it. And the rest of the variation is actually much smaller as compared to the variance along this direction. So this is the idea of principal component analysis. If we could rotate the data and find those new dimensions, and we could just drop the directions that doesn't carry or explain a lot of variance in the data. We keep those directions or eigenvectors that represent the majority of the variance in the data. So this is the basic idea. So we the goal is to project the regional data into a much smaller space, resulting in dimensionality reduction. We find the eigenvectors. Here we have two eigenvectors from the covariance matrix, and those eigenvectors defines the new space, and we can decide which ones to keep and which ones to eliminate. Similar ideas is presented here again. When you have a data point like this, when you directly project it to the x and y axis, you see they both carry some variance. But if you rotate your axis, your space, you rotate your space so that you have the new component 1 and 2, you will see that this component 1, when we project the data onto this direction, we captures almost all the variance in the data, because the other direction, if we draw perpendicular lines from the data points to this PC2, principal component number 2, we will see those dots almost overlap with each other. So we see in PC2 direction, the variance is almost 0. They're all the same, the data points. Therefore, keeping PC1 alone should capture the variance in the data very well already. And we should also notice that we simply rotated the axis. Therefore, this axis has to be, either of the axes is a linear combination of the regional axis. This has to do with the vector and the vector mathematics. So with that, we can talk a bit more on the steps. The steps is actually very high level in this class, as we are not a statistic class. The details you can find in any web resources or review your the content that you learned in your statistics class. But the idea is the key thing in principal component analysis is we have to normalize the input data. So the range of each attribute is roughly the same, because if we have different if data is not normalized, for example, if some attributes is measured in kilometers, other measured in centimeters, then the values measured in centimeters is going to have larger variance. It's going to carry more weight. That skewers the analysis. So therefore, we typically will do a z-score normalization to get the data into roughly the same range. Okay. And then the next step is to compute to find the eigenvectors. Those will be k. So k is our target dimensions that we want to get to. In typical principal component analysis, k would be less than, but most times equals n. We find all those vectors and then sort those vectors based on their loading. Loading is how much this direction explains the variation. If we have we have n new vectors or the eigenvectors identified, we will then be able to select the best component that actually explains. So here are the key orthonormal vectors, those are just the key principal components that we're going to find. So in this case, originally we have two-dimensional space, so we're going to have two principal components. Then we find that PC1 explains more variance than PC2, and we can decide to keep PC1 and drop PC2. So here we are going to compute PC1, PC2, and PC ... BCN, right? So we first find PC1 that explains the variance the most, and then we find a orthogonal vector that's orthogonal to PC1. That's going to be our PC2. This PC2 going to explain the most of the variance in the rest of the variance that's not being explained by PC1. So iteratively, we found all the PC ... n vectors. Those are orthogonal to each other. So all the k vectors going to be orthogonal to each other, meaning they are perpendicular to each other. They are also normal, means that their length is unit. So basically, those vectors only defines the direction. Okay. So like what we have here. Really, those two vectors defines the direction how we want to rotate this space. Then when we have those principal components identified, then every input data, our observations, original observations, by definition, would be a linear combination of those k components, because we did not do anything. We simply rotate this. So the vector, it was here, and now in the new space, because we rotate this, the vector going to be just a combination of the new components, a linear combination of the new components. And I mentioned earlier, the principal components that's being obtained are sorted in the order of decreasing significance or strength. the strength is measured by loading, so the amount of variance explained by this component. Because the components are sorted, we can actually then decide to drop certain components and reconstruct our data. And this data are going to have a smaller dimensional space. Let's use one example. So this is in your R exercise. I'm using the iris dataset. I'm removing the last column, which is species. This is not numerical, therefore we don't use it. We use the first 4, sepal length, width, petal length, and width. So we do principal component analysis and we show the loading of PCA. The result shows that originally we have 4 dimensions. Our principal component analysis will output also 4 dimensions. So component 1, 2, 3, 4, those are the 4 new dimensions. Those are the rotated axes in this 4-dimensional space. All those coefficients listed here are going to be useful. But let's first look at this SS loadings. This is the loading that explains relative importance of those different components. The sum of all those loadings together should equals to the number of the dimensions, so it should be equal to 4. This is a very special case that every component actually have exactly loading 1. Typically, it won't happen. So I'm thinking this iris data was artificially made. This tells us when the numbers are different, we know which component is more important than others. Okay, the result should show you that the most important component are going to be component 1, 2, 3, and 4 in the descending order. It also tells that proportion of the variance explained by this component. In this case, this is a very special case, every component had loaded a quarter of the variance. Therefore, the cumulative variance explained. So component 1 only explained a quarter. If we take component 1 and 2, then we would have explained 50% of the variance. If we keep the first 3 components, then collectively those 3 components should explain 75% of the original variance in the data. Then let's see, we're happy with 75 because our goal is to reduce dimensionality. We decide to cut dimension 4. In a typical case, the last dimension would carry very little. The SS loading should be very small. So we're pretty much happy with the first 3. So then we want to reconstruct the data by just using the first 3 components. We reconstruct the data using the coefficients in this table. Our original data would have the length. So species is going to have length, width, sepal length, sepal width, petal length, petal width. But now to convert the data into this new representation, we only have those 3 components as the features. Then component 1 is computed by using this. So those coefficients are used as the weight. So component 1 becomes this weight times the original sepal length plus, here we have a 0, so we can forget about sepal width. Now the next item we need to plus is 0.857 times the original petal length. And then we add the last item, which is 0.358 times the original petal width. Okay, so using this formula, we can convert the original observations into new values for component 1, 2, 3. It's simply done by calling create me a new data frame using the first 3 dimensions. So as you can tell now, we have the original iris data reduced Originally, we have 4 dimensions. Now we only have 3 dimensions. And the future analysis of this data set now using all those components, not the width length. This is the process that using PCA to reduce dimensionality.